Okay, so thanks for returning. So last time we jumped from 3 and 4 dimensions directly to 6 dimensions. And I mentioned that there are 2 classes of theories. For today, we are going to only use one of these 2 classes. So these are 62,0 theories. They are classified by ADE. What's the meaning of this? So we know that in some dimensions we can have gauge theory, and then the gauge group can obviously be a Lie group of either type ADE or something else. That's not what's happening here. So if we're in a gauge theory and we have a gauge group, they are going to be Wilson lines or particles, charge, and representations of the gauge group. But here, the charged objects are not going to be just lines or particles. Instead, they are strings. They have a 2-dimensional word volume. If you look at this at constant time, then you will see an extended object. So that's a string. In a theory that is labeled by, let's say, G of type ADE, then the strings will be charged and so it will be characterized by elements in the weight lattice. Again, you expect that this is modular action of the vowel group of G. And what can we do with these theories? So last time we ended with a particular geometry, which is either S1 or R1 times the 2 manifolds or Riemann surface sigma times 3 manifolds. So this is decomposing 6 into 1 plus 2 plus 3. The dimension add up again to 6. And what can we do with this? In this kind of geometry, we can reduce either this factor or this factor. What do I mean by this? I can shrink the size of the 3 manifolds. So therefore, the theory first looks like some 3-dimensional theory that depends on choice of M3 over here. And then we can study that theory. And then if I further reduce on S1, what we get is 2D QFT labeled by M3. So last time we have seen some 3D QFTs, right? And I think I already mentioned that if I take M3 to be a length space LK, 1, the 2D QFT is exactly this TT-formed version of the Verlinde algebra. And then a natural question is, well, one question that I ask is how to categorize this. One categorize this into some category that's supposed to be describing category of line operator in some 3D N=2 theory. But in this setup, you can ask a different type of question. So here we have specialized M3 to be a length space. What happens if I take a more general 3 manifold? So between length spaces and general 3 manifolds, there are like different layers. For example, I can ask first, if I just take M3 to be a cipher manifold, can we describe this algebra? And then can we describe this category? So they are all going to be labeled by the 3 manifolds. Well, what are they? I don't really know. That's a question for you. Alternatively, one can first reduce this factor, and then one will have either 4D theory, M3 times S1, or 3D theory of M3 if I further reduce the S1. And then here one can ask whether we can have some interesting 4D TQFT or 3D TQFT obtained by this, and they are going to be labeled by sigma. What I mentioned last time is that if I take actually sigma to be a disk, then we can reproduce the hat. So let me just say a bit more of that. So instead of really taking this to be a disk, we can actually just take this to be R2. That's slightly simpler. So in particular, there's not really a need to choose any boundary condition at this moment. And then R2 would have isometry. So I can have action of the U1. And then what happens if I look at the resulting theory? If I further reduce on M3. So I'm supposed to have some quantum mechanics along the R direction. So I have some quantum mechanics. And then the Hilbert space of this quantum mechanics are going to be contain some states that are generated by those strings. So if you think about it a bit, you'll realize that there's a subspace. I will just denote by A0, either meaning ground states or pseudosymmetric states. So this is this familiar subspace that we have encountered in 1D quantum mechanics, where the Hamiltonian basically has zero eigenvalue. So this is the statement is that this is given by basically strings. And strings are, as I mentioned before, two-dimensional. So and this is one direction, and then we need another direction. And that's supposed to be inside M3. So we will take some gamma, and that's inside M3. But the string has charges, so we can decompose this according to the charges of the string. So, and then for some reason, this only depends on homology class of this. And string can only contribute if it's representing a torsion class. So as a consequence, we can decompose this into HA. And then A here will be exactly the class of gamma inside homology of M3 with coefficient, let's say, in the weight lattice. And and this is only non-empty if we look at the torsion subgroup. So that's one way of seeing that. In this way, you get homologies that carry this A index. And furthermore, there is a U1 action that introduces another gradient if you decompose that into the eigenspaces of the U1 action. And there is actually another U1 symmetry, and U1R symmetry that is not directly visible from the geometry, but it's there. So therefore, it's going to be this double-degraded thing labeled by A. And that's exactly the categorification of Z hat. So this is a physical way of seeing that Z hat should exist and should be categorified. Namely, it should have integral coefficients. Again, this is not providing answer to like why it looks like character of a log VOA, but well, it's something. So if we take some other sigma, what would we get in general? So if we reduce on sigma, so sigma theory on sigma, then we will have for the n equals to 2 theory that I will just denote by T of sigma. And what can we say about this three-dimensional, let's say QFTs? So there is a general statement, but I don't know how useful this is. So the general statement is that this 3D QFT is a Rosansky-Witten model with target, the modular space of Higgs bundle on sigma. So this space is what we have seen before. This is modular space of GC Higgs bundles. And to again emphasize that this is not the Higgs bunch, I would write explicitly that this is also the Coulomb branch of the theory T sigma. So I will say more about what's the meaning of Higgs and Coulomb branch in a minute, but just remark that what's the meaning of the Rosansky-Witten model? So before we mentioned A model and B model as topological twists of 2D theories, and I even told you how to describe this A model to CP k-1. So that's given by a 2D QFT, and that's also within the algebra for U1 at level K. So Rosansky-Witten model is like the 3D version, but it's not the analog of A model. It's like a 3D B model. As a consequence, it's not detecting things like Fukaya category or quantum cohomology. Instead, the expectation is that if you look at what this Rosansky-Witten model associated to S1, so this is supposed to be some category. If we are in some transcending theory, this will be some modular tensor category. But now, this is expected to be some deformed version of the derived category of coherent sheaves on MH. So if you want to learn more about this interpretation, you can take a look at the paper by Roberts and Williamson, where they described deformed version of the derived category of coherent sheaves, and they argue that it's actually a braided Rubin category in the derived sense. So then that's quite close in toward building a 3D QFT. Well, but this well, in this language I could not understand it. So what I will do next is first describe this geometry concretely, and then in some cases understand some way of reducing this huge thing into something smaller. In some cases, into actually a modular tensor category. So if we take a general 4D n equals to 2 theory, T, not necessarily labeled by sigma. So here, what's the meaning of n equals to 2? So that means that the supersymmetry is not minimal. So what's the minimal thing? The Lorentz group, or let's work in the Euclidean world, is spin 4, E for Euclidean. And then it is a product of SU2 left times SU2 right. Supercharges are spinors. So the minimal thing is that you only have left moving spinors, but that's for some reason not allowed in a quantum field theory. You must have both left and right moving spinors. So you need at least 2, 1 plus 1, 2. This means that there are two types of spinors, one transforming as left moving spinors, another transforming as right moving spinors. So that would be these four spinors in the for the n equals 1 theory. For the n equals 2, you need two copies of this. And as a consequence, there's additional R symmetry. I will denote it as SU2 R. And then they are also going to be two-dimensional, from two-dimensional representation of the SU2R. So now there are 8 supercharges. So if we want to have a topological theory, we should have some nilpotent supercharge, namely Q that square to 0. So, but if you look at those Qs and linear combination of those, they will not just square to 0. But Witten come up with a very clever trick. He noticed that one can turn on some backgrounds for this SU2 at level R, turning on some fluxes and some connections. In particular, the connection, if you turn a connection such that it's spin connection associated with, let's say, the left moving spinor bundle, then there can be a supercharge that is nilpotent. So if you do this, then basically what you are doing is you are taking a subgroup SU2 left prime as the diagonal subgroup of SU2 left times SU2R. And then what happened is that sum of this will give you 2 times 2 equals to 1 plus 3, our familiar decomposition. And then this 1 actually means that there's a Q that is going to be a scalar here. That's the Q that squares to 0. So what I'm describing is that there is a way of performing topological trees to get 4D topological theory. But notice that this is not expected to be 4D TQFT in the usual sense, in the sense of Atelier sequence axioms, because we expect that potentially there are a lot of partition functions that are not well defined. And we will see more of this problem in a moment. But before that, is there any questions about this discussion? So if I'm given a 4D equals 2 theory, so I can ask what is the moduli space of vacua, and in principle I can ask this for any manifolds, moduli space of vacua, any 4 manifolds. But the common question is about moduli space vacua on R4. So that's a flat space. The quantum field theory are supposed to be defined on flat spaces. So what is the moduli space of vacua? So in general, there is going to be particular branch of this where the SU2R acts non-trivially. And then there's a branch where this acts trivially. The one that SU2R acts trivially is expected to be the Coulomb branch. So, and then there are other branches. For example, there is a branch where the SU2R acts non-trivially. That's the Higgs branch. And then there are also potentially other branches. Maybe look like this. These are usually referred to as mixed branches that somehow interpolate between these. So to maybe distinguish between Higgs branches and mixed branches, it's useful to notice that there is another U1 symmetry, another R symmetry that I would denote by U1R that acts on the supercharges with charge plus and minus 1. So it acts with charge plus 1 on the left moving guys and charge -1 on the right moving guys. And then the Coulomb branch and the mixed branches are going to be acted upon by this U1 R symmetry. So this is roughly how the model space of vacuum looks like in when you put the theory on R4. So the Coulomb branch will play some special role for us. So we will have the denoted by the symbol BT. So that's the Coulomb branch. And then you can also ask the question, not on R4, but another space that emit a flat metric. You can ask what is moduli space of vacuum on S1 times R3. And that's again flat, and for any quantum field, you should be able to put it on this geometry and ask what is the moduli space of vacuum. And then this again will have different branches, and we'll be looking at the Coulomb branch again, and we'll denote it by MT. So now this Coulomb branch will have actually different dimension than the Coulomb branch over here. In fact, we'll have a vibration. So the Higgs branch in 4 dimensions, this is expected to be hyperkähler. The Coulomb branch is expected to be only Kähler, but with some special property. So it's special Kähler in somehow a precise sense. But then the Coulomb branch in 3 dimensions, or in S1 times R3, that's again hyperkähler. And then the fibers are special Lagrangian tori. And I'm sure this already remind you of the Hessian vibration that we talked about before. So let me.
BT is also the Coulomb branch. So
Yeah, that's the Coulomb branch on R4. And the point is that if you consider the Coulomb branch on S1 times R3, become a bigger space, and one fiber over the other. So let me give you some examples. So the basic example is the free theory, gauge theory, U1. So for this theory, B will just be the complex plane. And then this guy will always be twice the dimension. And it will be the total space of C times T2. So in this case, the vibration is completely trivial. And that's another way of saying it's actually a free theory. So free geometrically just means trivial vibration. But this Coulomb branch is not just a real manifold. It's supposed to be a hyperkähler manifold. So you also need to specify what is this T2 as an elliptic curve. So this, another way of saying this is that this theory is there's one parameter family of theories, and they are labeled by something, either a complex parameter or viewed differently, they are labeled by an elliptic curve. And what is this T2? It will be a Jacobian of this elliptic curve. So for people who know a bit physics, what's happening is that this is going to be parameterized by a complex parameter tau, and then you can decompose that into the real and imaginary part, and those are related to the gauge coupling and theta angle of the free theory. But so this is a very simple Coulomb branch. So any question about this particular Coulomb branch? Yes.
I don't know if it's at all possible that quickly maybe explain, for example, how we would calculate the Coulomb branch on R4. That this is in this case just complex line.
Yeah, so this is a U1 theory, and then there is a particular representation of that algebra known as vector multiplet. So in that multiplet, there is a gauge field, some fermions known as gauginos, and then a complex scalar phi. So this is a complex. And then on R4, you can ask what is the vacuum expectation value of this guy phi. That's a number. And if the number is different in one vacuum versus another vacuum, then they are different. In other words, different vacua, in this case, actually, it's being parameterized by this expectation value. So this is exactly what's parameterizing this Coulomb branch on R4. Okay, so what are those? Those are now related to line operators. In the theory, they are going to be Wilson lines that are so we can just look at the Wilson line labeled by the representation with charge 1. There are actually a different kind of line known as the tooth lines associated with magnetic monopoles. And then if we put this on S1 times R3, you can ask what is the expectation value of this line when I wrap it on S1. And those are parameterizing the longitude and meridian of this torus. So is that answering the question? Okay, so either way that I can explain this so that you understand it slightly better. So this is a physical way of seeing what's happening. But for now, you can just view this Coulomb branch as a substitute for the physical theory. Just think of those theories in terms of the geometry. That's completely fine. Okay, so this is a free theory. Another free theory, generalizing this one in a somewhat boring way, is a high rank U1 gauge theory, high rank abelian gauge.
What is Higgs branch in this case?
Yeah, in this case, there's no Higgs branch. It's just empty or regarded as a point. So here, there's only vector multiplet. There's no hypermultiplet. So there's no Higgs branch. So another example is U1 to the G. So I'm taking G copies of this. And then it's not surprising that I'm just having G copies of that Coulomb branch. So MT now is just C times T2 to the G's power. So I don't know how to draw this, but well, if I draw it, it will just exactly look like that one. But with understanding that this is C to the G. And then this one is supposed to be S1 to 2G. But again, this is a hyperkähler manifolds. So there's some complex structure over here. So what shall we do? It can be a general abelian variety, but we'll consider a special family labeled by genus G Riemann surface. And then this will now be the Jacobian again of sigma. So Jacobian of genus G Riemann surface will be a complex abelian variety of compact dimension G. So that's perfect for this guy.
What is corresponding VOA?
It's either BC or beta gamma system, right? In this case, and then you have G copies here.
Oh.
So this is a very simple theory. And because the vibration is trivial, again, it's a free theory. So to have a non-free theory, we can consider the following example. So I will refer to it as the monopole. It's the base is still one-dimensional, but then the vibration is going to be non-trivial. So it's not a free theory anymore. Over a generic point, you still have elliptic curve, but then over this special points, you are going to have degenerate elliptic curve. And this is in Cordilleras classification, an I1 singularity, such that if you go around it, you will have monodromy given by the T transformation. So in this case, there is actually a Higgs branch, but it's again a point. You can view that just as something sitting here. Well, so this theory, sometimes we view this as a conformal theory, but it's in a sense very bad as a conformal theory. So, but this may not mean that there's no VOA associated with it. There could be, but I don't know exactly what it is. It is perhaps something very simple. So what all these theories have in common is that they are all abelian theories. So what's the meaning of that? So for some of the theory, they might have Lagrangian description. I will not define this word precisely, but I will just say that it's specified by a choice of gauge group and then another choice of a representation. So here we have G being either U1 or maybe C star, so whatever notation you want to use, and then N being trivial. In this case, it's when G equals to G copies of C star, and again when N is trivial. So in this case, it's when G equals to C star, and then when N is actually natural representation with weight 1 of the C star. So next example is non-abelian, but it's not abelian in the simplest way. It's SU2 supramu theory. So then G equal to either SU2 or SL2C, and then N is still empty. So what is this theory? The Coulomb branch. The 4D Coulomb branch, or B, is still the complex plane, but as I mentioned before, it's a Taylor manifold. So there are two special points where the metric becomes singular. And then over a generic point, you are still having an elliptic curve. But then over this, you are again having this degeneration. So there are, in other words, two I1 singularities.
So what is sigma?
Oh, in this case, it's a bit hard to characterize that by sigma, but still you can take sigma to be P1, but with two very special singularity. So then the monodromy of this will be conjugate again to the T transformation. So you see that this geometry, it has a property that in a sense it contains two copies of this. And this leads to a very famous conjecture known as Witten conjecture, telling you that the Donaldson invariance is in a sense two copies of the Seiberg-Witten invariance. So in other words, there's a way of relating the TQFT that you obtain from this with the TQFT that you obtain from this. And then for the monopole theory, not surprisingly, you get either the monopole equation or alternatively known as the Seiberg-Witten equation.
And what is Higgs?
So in this case, it's again, well, it's just a point. So yeah, it's in a sense empty. So, but well, I don't know. You can still draw two points there too. Yeah. Okay. So this example is quite different from the previous examples because before we always have some U1 action rotating the base. But here it's hard to come up with any U1 action that acts naturally. Also here and over there. So this is one geometric way of distinguishing between conformal versus non-conformal theories. So this will be non-conformal. This is again related to the fact that this U1 and somehow the conformal transformation are going to be related in a superconformal algebra. So from now on, we'll actually just focus on conformal theories. So they will always have this U1 symmetry that acts on the base. So any question? So one theory that is actually expected to be non-Lagrangian, so which means that I cannot write down the G and N. It's known as Minehan-Nemchansky's E6 theory. So in the name, there's E6, but G is not equal to E6, and then there's no N. But what happens is that, so the base is still one-dimensional, but the fiber, the singular fiber, looks like the affine E6. I hope I got it correctly. And then this is actually conformal theory. There's more general class of theories labeled by Riemann surfaces. So that's well, the class of theory that I have been keep talking about. So the proper name for them is class S. So you have already heard about it if you were here last week. And those theories are labeled by sigma and also G, now assumed to be of type ADE. So I will often just omit the G when it's obvious. And in fact, here one can allow sigma to have marked points. So in particular, if you take sigma to be sphere with 3 marked points and G to be SL3, then you can get back this example. So this is a special case of general class Z theory. For general class Z theory, the Coulomb branch will just be the moduli space of Higgs bundles. And then you know the rest. It has a Hessian fibration. And then the fibers are indeed special Lagrangian tori. Maybe the simplest one is S1 times S3. So what is this? This is counting the dimension of the Hilbert space that you associate to S3. And if you think a bit about this, this Hilbert space can be identified with space of homomorphic functions or regular functions on the base of the Coulomb branch. But this guy generically is not compact. So this space, therefore, is generically infinite dimensional. So if we just take this to be C, then what is the space of homomorphic functions? 1 is a function, Z is a function, Z squared is a function, so on and so forth. If you add all of these up, you get 1 plus 1 plus 1. So this is, well, infinity. So what can we do? So, so I mentioned that for conformal theory, there is a U1 action. And the U1 should have the property that actually there are no fixed points when it acts on BT. So this, the U1 fixed point should be just a special point O sometimes referred to as the superconformal point. So can we use this to regularize this? So if we are allowed to compute the character of this U1 action, then instead of having 1 plus 1 plus 1 plus 1, we're going to have 1 plus t squared plus dot dot dot. And then we can sum this up to be 1 minus t, 1 over 1 minus t. So could this be a solution to this problem? Namely, well, I still don't know how to regulate this on 4 manifolds, but can I just consider S1 times M3 and then use this S3 to somehow turn on this symmetry to have a well-defined answer? So unfortunately, this could not work. So first of all, you should not expect this to work because, well, if this can work, this means that we are going to have a family of 3D T QFTs parameterized by T. And no one have heard about 3D T QFTs or more than tensor categories that can be continuously deformed. So there should not be such a family. And from the physics point of view, the problem with this is that this U1R, this U1 that we are using, this is R symmetry. And it acts naturally on supercharges, and that's somehow illegal for this purpose. So this can only work if M3 is ciphered. But then it's not really a 3D T QFT in any way if you can only define it on cipher manifolds. But alternatively, you can fix this cipher manifold and ask what happens if I change my sigma. And then that's the 2D T QFT labeled by 3 manifolds that we started with. So that's exactly the T there that we have seen yesterday. And then if we take this with length space, then we are getting back exactly to what we were previously. But that's not what we are interested in doing today. We are interested in having more general 3 manifolds. So is there any some other scenario where we can have some luck? It turns out that there is another situation where we can do something. So the U1 action that acts on the Coulomb branch, I will say U1 Coulomb, is actually in general covering of the naive U1 R symmetry. And it can be an n-fold covering. In all the previous examples, we always have n equals 1. But that's just one possibility. So there are 2 possibilities. One is that n equals 1. The other possibility is that, as you can guess, n larger than 1. Do we have some theory whose n is larger than 1? And can we do something with those theories? Now, what's a nice property of this is that by definition, you will act truly on supercharges because it's if you map it here, it becomes 0. And this is something that acts on supercharges. So can we have some luck working with this class of theories? First, do they exist? So then this is example.
It is not a representation of G. It is a number or representation of G.
Oh, n here is just a number. So maybe I should use something else.
It's not the same.
Yeah, it's not the same n. So I just maybe f. And f larger than 1. So are there theories such that we have f larger than 1? So there are, even when the base is 1-dimensional and the entire Coulomb branch is like 2 complex dimensional or 1 quaternionic dimensional. So these are rank 1 Julius Douglas theory. Their multi-space always looks like this. So the base is again one-dimensional, and there's only one singularity. And then over that, you have some singular fiber. So in one case, it looks like this. In another case, it looks like this. In another case, it looks like this. And in Cordairas classification, so this is this one is type 2, 3, and 4. And you can write down the monodromy matrices. So, for example, this is 1, 1, minus 1, 0, and 1, minus 1, 0, 0, 0, 1, minus 1, minus 1. So these are possible Coulomb branches, and there's nothing wrong with those Coulomb branches. Then they have non-trivial ZF action. So here, these have a Z5 action. So there's a Z5 that actually acts in a way that it preserves the hyperkähler structure. So before this U1, it will not preserve a hyperkähler structure, it will rotate it. And that's another way of saying that it's an R symmetry. But this will actually preserve the hyperkähler structure. Then here, Z3 and Z2. So these Atelier theories has names. So there's a large family labeled by a pair of ADE thinking diagrams. And this is A1, A2. This is A1, A3. And this is A1, D4. And for very large families, well, for Atelier theory, they always have F larger than 1. So you can get a lot of theory like this. So where is the eraser again? Oh, here. Then you can ask in those classes of theories, can you indeed use this to regularize the partition function? And our observation is that this seems to be always possible as long as, so when the action of ZF on the base is again just the origin, then it seems that there's no singularities or infinities that arise. We can get either 3D QFTs or model tensor categories. So this is supported by some commutation. So then we propose this as a conjecture together with Sergei Gukhov, Hirako Nakajima, Nikolai Dedushenko, and Ke. So if you are interested in this, you can take a look at our work. So here, before we have, if we have this U1 action, we are dreaming about having like C-star family of 3D QFTs. So here, of course, this will not be a C-star family, but it's supposed to be ZN or ZF star family. But that's more natural. C-star family of MTCs are something that you will not dream of. But ZF star families are natural. These are Galois orbits of model tensor categories. So let me tell you what it should be in this case. So in this case, physically, what you can do is that you do some commutation, and then you can find the S and T matrices for the relevant MTC. So in this case, if you compute, you'll find S to be and sine pi over 5, sine 2 pi over 5. And then for T, given by exponential of 11 pi I over 30 e to the minus pi I over 30. So Are there any model tensor categories that correspond to these SNT matrices? The answer is yes, and it's a famous one. It's the Young MTC. So it's associated with the Young VOA, which is the 2,5 Virasoro minimum model. So this MTC has two simples, so 1 and 5. And then the fusion rule is this famous Fibonacci fusion rule. So phi squared equals to 1 plus phi. So in general, if I have some geometry, how can I figure out SNT matrices, and how can I figure out, let's say, the number of simple objects and what is the MTC that I should get? There is a dictionary, so it's quite incomplete, and it's still being in the process of being discovered. So if you want to find simple objects, then geometrically, these correspond to the fixed points over the entire space. So in this example, the two fixed points are here and here, and they are associated with 1 and phi. How about T matrix? So T lambda lambda associated with a simple object lambda. Geometrically, this is related to the value of the moment map. This U1 action is actually a Hamiltonian action generated by some real value function. And you can evaluate that on any of the fixed points. And there's a dictionary going from the value of the moment map to the T matrix. And the S matrix is related to the weights of the S1 action, or just like U1 action on the normal bundle of lambda. Let me just write nu lambda to denote the normal bundle. And how about other things? So there are some hints that for the fusion rules, they correspond to equivariant quantum K theory of the entire space. And then I have no idea how to get F and R matrices. So these are potentially questions. So how to get those geometrically. So what is actually going on here? So why we are getting this particular model tensor category? So as you have heard from Tomoyuki last week, for superconformal theories in 4 dimensions, one can get some VOAs. And the 2,5 minimum model is exactly what you get here. This is, but as you heard last time, there's a close connection between the Higgs branch of the theory with that chiral algebra. But somehow the Coulomb branch also knows a bit about the category of modules of that algebra. And in fact, this connection between Coulomb and Coulomb branch and the VOA seem to be slightly more general. So it seems that there is some connection between the category of modules. So with this chiral algebra, so here I use chi T to denote this VOA that you get from superconformal theory T. It seems that there is some connection between this. And then let's say the geometry of the Coulomb branch or derived category of coherent sheaves on this Coulomb branch MT. And then this is indeed what Rozansky-Witten model would associate to the circle. And in general, we don't know how to deal with it. But experimentally, in those cases, we know that we expect that there's a way of reducing this to a smaller category. That's this model tensor category, maybe Zn family of it, Zn star family of it. ZF. So experimentally, there's some reduction like this, getting nice MTCs. And then there's seem to be also connections between this MTC and the category modules. But here there are two question marks. In general, I don't know what is this geometric process that go from this complicated category to a nice MTC. Also here, in general, the stories seem to be more complicated. In this case, it's somehow just given. They are just the same. But in general, it seems that some non-trivial reduction is also going on. Even more mysterious is to say something about this connection. And this connection seems to even exist when there is no such a reduction to nice model tensor categories. So let me give you some examples. So in particular, actually, this is an example. So what is the VOA associated with this? This is E6 at level -3. Then there is category O for this VOA. And then in that category, there are 7, sorry, 1, 2, 3, 8. Sorry, am I counting this correctly? 7, right? Nice highest weight modules that correspond to exactly these 7 fixed loci under the U1 action. So here, if you look at the U1 action, there will be 6 higher fixed points, and then this entire component is going to be fixed. And then you can relate the fixed points to highest weight modules in the category O with this F&D algebra. That's somehow generalizing this dictionary to the case where we don't have a very nice MTC.
Which one corresponds to the middle?
It's actually not terribly special. So this is something that confuses us also slightly. So there's a special one associated with the affine node that corresponds to the vacuum module. But then I don't know how to distinguish between them over here. So it seems that that one is not terribly special for some reason. Yeah, it would be great if you can find a way of just say like why it's different and how somehow like why in this category you see that it comes from a higher fixed loci of higher dimension. So this is a family of theories, right? So there is Minnan-Handam-Chansik is E7, E8 theory, and the VOA associated with them are respectively E7 at level -4, E8 at level -6. And again, this dictionary will hold. We look at fixed loci on the Coulomb branch, they correspond to highest weight modules in category O. And then that also works for SO8 at level -2. And maybe you can even further degenerate. So this relation can be checked in a lot of theories. Either have this F number larger than 0 or equal to 0. In the world of Azure-Stogler theories, so let me provide you with a table. So one can look at, for example, A1, A2N theories. So they generalize this family. And the VOA associated with them are 2, 2N plus 3 minimal model. And then you can check. So let me maybe erase this part. So F in this case will be 2n plus 3. And then you can check that indeed the number of fixed points correspond to simple objects. And you can also match the relevant data for S and T matrices. I will just give the number of fixed points. In this case, it's m plus 1. This is something that you exactly expect. Another class of theory is A1, the 2n plus 1. So they actually generalize this family because A3, that's B3 as well. So for this family, you have affine Casimudi, SL2 at level -2 plus 2 over 2n plus 1. F would be 2n plus 1. And then you can check the number of fixed points. That's 2n plus 1. And if I understand correctly, there's a way of going from the category of modules of this to some smaller category where there are exactly 2n plus 1 simple objects. And then for A1, B2n, so the kind of algebra in this case is certain Wn algebra. It's some non-regular quantum Hamiltonian reduction of SL n plus 1 at level -n-1 squared over n, and F here equal to n, and then the number of fixed points here equals to n squared. And I think several years ago when we first looked at this, we compare this with some data that is in Thomas' paper, and I think there is agreement. Yeah. I hope that hasn't changed. And then there's also, there's also A1, A2n plus 1. So this is again something that you can find in Thomas' paper. So it's M plus 2 algebra. It's a certain subregular reduction of again SL n plus 1 at certain level, and there again there is some agreement. So F equals to n plus 2, and number of fixed point equals to n plus 2, n plus 1 over 2. And you can check more examples. So these are the interesting A1 series. You can also check the interesting AN comma A. So let me hope this is not too low. AN minus 1 comma A K minus 1 examples. So those will be certain minimal models for N, so N plus K minimal models of Wn algebra. Then you can check that the number of fixed points on the Coulomb branch also match exactly the number of modules over there. So it seems that this is some robust and interesting correspondence. So just one remark about this relation. So this is something that should remind you of symplectic duality in 3 dimensions. So why would I say that? So in 3 dimensions, if I reduce the theory, the Higgs branch will not change. So there is an interesting connection between the Higgs branch, and as we have learned, it's closely connected, and in fact can be recovered by the chiral algebra itself. And then there's the connection between that and the Coulomb branch. So this is often known as symplectic duality, telling you that singularities of symplectic manifold always come in pairs. So if you want to understand how this deform, that's related to certain symmetry on this side. So now this seems to be analog of the symplectic duality, except that first of all, it's in 4 dimensions, and then it's more categorical than the original statement. So this is something that we sometimes refer to as the 4D symplectic duality. So it would be really nice if there's a way of correctly formulating this, and then the test will prove this in more generality. So let me end here, and thank you all for staying through.
Yeah, thank you very much. Do we have some questions? Simon?
So I tried to look it up while you talk. Can you maybe explain, is there a relation between this bundle, I don't know what this thing is, the bundle of Higgs bundle modular space and string of fiber input and tone? Isn't that what the debate?
Well, there is some connection, but I don't know how to explain that simply. So, there are different notions of Neapolitan cone. So here, Neapolitan cone, right? So in the context of Higgs bundles, then the Neapolitan cone is about this fiber at the origin. So there's a most singular fiber, and that's a Neapolitan cone, right? And then for classes of theories, so let me maybe clarify that I use the notion of class I theories, and this is a class I theory. I mentioned that if I take P1 with some singularity, that's giving exactly this. But how about the addressed object theories? So these are theories that are slightly unusual. You can still view them as class I theories, but instead of having usual Riemann surface with marked points, you only have P1, and then with some potentially very bad irregular singularity, and then maybe another regular singularity. So in that way, you can interpret this as a Higgs bundle. It will not be usual Higgs bundle. We sometimes refer to it as a wild Higgs bundle. And then that geometry has some relation with Springer fibers in some of the families. I don't know what's actually the precise answer. So.
Should ask a question. So I understand in your theories that you only see highest weight modules, but do you know whether the highest weight modules that you see are simple? Do you have like a Schur index for modules which allows you to check this?
Well, I think that's a question that I would ask either you, Thomas, whether in the highest weight module in this category O, whether they are simple or not.
They're not in general.
Yeah. Right. Then, so in this case, this will not correspond to nice simple objects.
Well, I mean, they have simple quotients, so.
Yeah. So I think, I think that's a great place to start to understand this connection. So here it's not exactly clear, like what's the way to formulate for this symplectic duality. It's, I think, a good starting point to understand whether fixed point corresponds to just highest weight modules or indeed these simple quotients or something related.
So, related question, do you have a way of getting at the characters corresponding to these?
The characters?
Yeah, I mean,
right. So, yeah, so there's a way of getting first the vacuum character in the theory. That's the particular superconformal index known as Schur index.
Yeah.
And then one can also try to do something to get characters associated with these fixed points. So far, it's not exactly clear what's the thing on physics that one should do. So I would guess that starting from this, one should get some certain either line operator or surface operator to be inserted. But it's not clear what's the exact operator that is needed. So yeah, so that would again be a very useful thing to have that will help a lot with understanding this connection.
So you are saying that you have a whole family of MTCs, but now it seems that always one special member of this family is selected. Like in this 2,5 minimal model, there are also other members. that are also, for example, realized by VOAs, are they also somehow visible? For example, do you have a modified and sure index for those? Or?
Yeah, so the observation is that in this family, there is always a special one. So we have CT. In principle, it's labeled by gamma, where gamma is multi-valued, but somehow only this guy has a very clear connection with the category of modules of the VOA. So there's some connection here. So for the other guys, I don't know how to interpret that in the VOA language. It seems to just be some family of Galois orbits of the original guy.
Without any interpretation, I mean.
Without a very clear interpretation to either Higgs branch or this chiral algebra.
Is there cases where the VOAs you get are these logarithmic finite VOAs?
So in this, okay. So in this case, we haven't encountered such example yet. I would guess that maybe you also, to get a lot of VOAs, maybe you also want 4D theories that are also more exotic. And I don't know which direction to go.
But the Bn+2 and the your type A1, D2n and A2n+1, they are logarithmic.
Oh, they are already logarithmic?
Yeah, already logarithmic. And I think this happens because the dual Coxeter numbers are not co-prime. Then you have these irregular singularities, and they seem to be related to that the associated VOA is not rational, but just logarithmic.
Oh, I see.
So in fact, also in your very last example, you are saying here you have this AN-1, K-1 theories, and you only get this minimal model if N and K are co-prime.
Right. So
and otherwise you also get a logarithmic one.
Yeah, I see. So right. So here actually so this is supposed to be a list of that we can compare with MTCs, and here I would assume that it's co-prime, but in general this relation. So I now remembering exactly whether this association works for NK not co-prime, but maybe it should still.
If it's not co-prime, you get higher rank analogs of this BN algebras, and they are related also to. I mean, they allow nice screening realizations in the spirit of Schoma and Zilong.
I see. So there it's already like tested that for this series of geostochrostic theories, those are correct VOAs associated to them.
Yeah.
Oh, okay. Yeah.
But nothing is known about these VOAs except that you can match sure indices.
Yeah. I see. So right. So here in the table that we only know how to compute the number of fixed points when it's co-prime, and that's where we have tested this. Yeah, but indeed, if you just ask for VOAs that are logarithmic, then yeah.
By the way, these BN algebras are very closely related to the 1,n singlet algebras. Is that a coincidence? I mean,
well, I would know the answer to this. The only thing I know about this algebra is that there are a lot of useful things in your paper about them.
Yeah, no.
We find these numbers.
I meant you're saying, right, it would be nice to get an intuition why the VOAs for three manifolds appear. And so my question is more, is there any relation between the A1, A2n+1 theories? And anything that you can say about?
That's an interesting comment, but somehow I have feeling that they appear on different sides of this reduction. So on one side, we get Q series labeled by three manifolds. On the other side, we get like interesting either VOAs or MTCs or other categories labeled by this kind of singular Riemann surface. So it seems that they somehow live on different sides, and I don't know whether there should be any connection.
Yeah, Probably not, because otherwise somebody would have said.
Well, yeah.
So yeah, now I would say we thank everybody for being here for the 4 weeks, and this was, I think, a really nice time. So everybody, thank you for coming, and especially thank you to our nice lecturers and the good job that we've done.
So being the last speaker, I have this honor or responsibility of asking all of you to thank our amazing organizers and also staff member at CRM. So thank you all.